Namaste children. How are you all? I hope you are fine. In the last class we have discussed Euclid's division lemma from our chapter real numbers and its applications we have used, and we studied where we use that Euclid's division lemma especially to find the highest common factor, that is HCF of numbers, and to study the properties of numbers also we use that Euclid's division lemma. The second theorem, it is a fundamental theorem of arithmetic. Today we are going to discuss fundamental theorem of arithmetic. So what is fundamental theorem of arithmetic? It is every composite number can be expressed or factorized, as a product of primes. Primes means it is prime factors here, it is, or prime numbers. So the prime numbers which are in the form of factors are called primes. And this factorization is unique, so only in one way. Unique means one way, one. We can write in one way only that factorization of the prime factors for a natural number or for a composite number, apart from the order in which the prime factors occur. So we can write the prime factors in any order. If we write in any order also, we can write in one way. To that to a composite number, the prime factors can be written in such a way that the prime factors can be written as the product of the primes in only one way. See, for example, we will discuss for example here. For example, 10. You see, what are the prime factors of 10? 2 5s are 10. So 10 can be written as what? 2 into 5. 2 into 5. We can write only 10. The prime factors for 10, it is only 2 and 5 only. 2 and 5. So this 10 also we can write the other way. 5 2s are 10. That is 10 is equals to 5 into 2. So here the order is changed, but in both the prime factorization, they have the same prime factors. Even if you take 20, it is 2 ones are 2 10s are 2 5s are. So 20 can be written as what? 2 into 2 into 5. 2 into 2 into 5. If you take it is 30. If you take 30 can be written as 2 1s are 2 5s are 15 2s are 30 and 3 5s are 15. So it is 2 into 3 into 5, that is 30. So similarly for 30 also we can find the prime factors starting with 3. 3 10s are 30 and 2 5s are 10. 2 5s are 10. Now here 30 is equals to 3 into 2 into 5. 3 into 2 into 5. So in the order of the prime factors here for 30 it is 2 into 3 into 5. Here it is 3 into 2 into 5. See, apart from the order in which the prime factor occur, but it can be factorized or expressed in the unique way, that is in only one way. It means that they contain only the prime factors will be the same. However, you are finding the prime factors. So the prime factors of 30, it is 2 into 3 into 5 or 3 into 2 into 5. It has same factors are there, but we wrote in the different order also. Same factors will be there. So that theorem is known as fundamental theorem of arithmetic. Fundamental theorem of arithmetic. So here we are using the concept of prime factorization. So now what is the application of this fundamental theorem of arithmetic? This we use to find the LCM and HCF of two numbers or more. So to find the LCM and HCF of two or more than two numbers, we use the fundamental theorem of arithmetic, and also we use this fundamental theorem of arithmetic to study the properties of numbers. Now we will discuss how to find the LCM and HCF for given numbers using the fundamental theorem of arithmetic. Using the fundamental theorem of arithmetic is nothing but it is prime factorization. Is it clear, children? What is the fundamental theorem of arithmetic and where we are using this fundamental theorem of arithmetic? It is. Is it clear? Yes. Now we will discuss exercise number 1.2. The first bit. Express each number as a product of its prime factors. What are prime factors? Prime in the sense it is prime numbers. The factors which are in the form of prime numbers are known as prime factors. So what are prime numbers? 2, 3, 5, 7, etc. Why these numbers are known as prime numbers? The numbers which have only two factors, that is 1 and itself, are known as prime numbers. What are composite numbers? the numbers which have more than 2 factors are known as composite numbers. We have studied in the lower classes prime numbers and composite numbers. One is neither prime number nor composite number. Now we have to find the prime factors for 140. The first sum it is prime factors for 140. So to find the prime factors, here we use the divisibility rules for 2, 3, 5, etc. So 2 is the first prime number. So which numbers are divisible by 2? What is the divisibility rule for 2? It is so if in the units place of any number is either 0 or 2 or 4 or 6 or 8, such numbers are divisible by 2. Therefore here in the units place we have 0 is there, therefore this number is divisible by 2. Divide with 2. So 2 sevens are 14. 14 minus 14 it is 0. Then bring 0. 2 zeros are 0. Again 0 is there, divide with 2. So 2 threes are 6. 7 minus 6 it is 1. Then bring 0. 10. 2 fives are 10. Here in the units place we have what is there? Here it is 5 is there, therefore it is not divisible by 2. Next test with 3. What is the divisible rule for 3? Sum of all the digits of a number is 3 or a multiple of 3, then that number is divisible by 3. And 3 plus 5 it is 8. 8 is not a multiple of 3, therefore 35 is not divisible by 3. Next prime number it is what? 5. So with the 5, so what is the divisible rule for 5? It should be in the units place it is 0 or 5 is there, then such numbers are divisible by 5. That is 5 sevens are 35. Last number, see that we got 7. 7 is a prime number. Last number we should get a prime number, then our prime factorization is over. So I have started with the 2. As here in the 140 0 is there in the units place, you can also start with what it is 5 also. So that it is depending upon us. So therefore 140 prime factors of 140 it is 2 into 5 into 7, that is equals to 2 square into 5 into 7. 2 square into 5 into 7. So this is the prime factorization of 140. Now 3825. 3825. Now you see in the units place we have 5 is there. So directly you can divide with the 5. The divisible rule for 5 it is in the units place, if it is 0 or 5 is there, then the numbers are divisible by 5. So 5 sevens are 35. 38 minus 35 it is 3. Bring to 32. 5 6 are 30. 32 minus 30 it is 2. Then bring 5 25. 5 5s are 25. Again here we have 5 is there in the units place. Therefore it is divisible by 5. So divide with 5. 5 ones are 5. 7 minus 5 it is 2. Then bring 6 26. 5 5s are 25. 5 5s are 25. 26 minus 25 it is 1. Then bring 5 it is 15. 5 3s are 15. 5 3s are 15. Now 153 we got here. Check. So 3 is in the units place, therefore it is not divisible by 2. It is not divisible by 5. Next test with the 3. So what is the divisible rule for 3? Add all the digits. 1 plus 5 6. 6 plus 3 it is 9. 9 is a multiple of 3. Therefore 153 is divisible by 3. So divide with 3. 3 5s are 15. 3 5s are 15. 15 minus 15 it is 1. 3 1s are 3. 51 we got. Again 5 plus 1 it is 6. 5 plus 1 it is 6. Therefore it is divisible by 3. So divide with 3. So 3 1s are 3. 3 1s are 3. 5 minus 3 it is 2. Then bring 1 17. So bring 1 it is 21. 3 7s are 21. 3 7s are 21. So what is the last number we got? It is 17. 17 is also a prime number. Therefore the prime factorization of 3825 is equals to 5 into 5 into 3 into 3 into 17. That is 5 square into 3 square into 17. So like this we will find the prime factors for 3825. Is it clear, children? Now we will discuss how to find the LCM and HCF of the given numbers using the prime factorization method. Is it clear? Now HCF of the numbers, given numbers, is product of the smallest power of each common prime factor in the numbers. So when numbers are given, we should find the prime factors of those numbers and write the prime factors in the exponential form, that is power notation. Then observe that is if more than one prime factor is there, then we should take the product of the prime factors with the smallest power. That is the common factors only should consider to get the HCF. Whereas LCM, it is product of the greatest power of each prime factor involved. Here it is not common factor. Prime factor, it is each prime factor is the product of the greatest power of each prime factor involved in the numbers is the LCM. Whereas HCF is the product of smallest power of each common prime factor. Here it is just a prime factor. That is the difference between HCF and LCM. Now we use this while we are finding this LCM and HCF of the given numbers. Similarly, we have studied in the lower classes for two numbers. Product of two numbers is equals to HCF and LCM of those two numbers. HCF into LCF. Now, if you want to find LCM, transpose HCF to here as it is multiplying, therefore it divides. Hence, LCM of two numbers is equals to LCM of two numbers. This is for only two numbers. LCM of two numbers is equals to product of two numbers divided by HCF. Product of two numbers divided by HCF. Similarly, if you want to find HCF, transpose LCM to the left hand side. We get it as it divides. Therefore, HCF is equals to product of two numbers divided by LCM. So, for two numbers, if you want to find HCF, when we know the product of two numbers, we will divide the product of two numbers with the LCM. So these four we use in solving the problems related to this exercise number 1.2. Now we will discuss the second bit from the first 1.2 exercise. Find the LCM and HCF of the following pairs of integers. Pair means it is two. So two integers are given and verify that the product of LCM and HCF of those two numbers is equals to product of the two numbers. So what are the given numbers? The second bit we are discussing, 510 and 92. First find LCM and HCF, then find the product of this, verify that LCM is equals to HCF into product of the two numbers. So now what are given numbers? Here it is given numbers is equals to given numbers are, what are the numbers? 510 and 92. Now the first step is find the prime factors of each number. So 510 is equals to what it is? What are the prime factors for 510? See here the units place we have 0 is there. So we can divide with what it is? 2. Divide with 2. So 2 2s are 4. 5 minus 4 it is 1. Then bring 1, 11. 2 5s are 10. Bring 11 minus 10 it is 1. Then bring 0, 10. 2 5s are 10. Again the units place we have 5 is there. So it is divisible by 5. Divide with 5. 5 5s are 25. 5 1s are 5. 51 we got. Units place 1 is there. It is not divisible by 2. It is not divisible by 5. Check whether it is divisible by 3 or not. 5 plus 1 it is 6. 6 is a multiple of 3. Therefore it is divisible by 3. So divide with 3. 3 1s are 3. 5 minus 3 it is 2. Bring 1, 21. So 3 7s are 21. So what is the prime factorization of 510? That is 510 is equals to what it is? 2 into 5 into 3 into 17. Here no prime factor is repeated. Similarly, find the prime factorization for 92. Find the prime factorization for 92. Here we have 92. 2 is there in the units place. So it is divisible by 2. That is 2 4s are 8. 9 minus 8 it is 1. Then bring it is 2. It will get 6. 2 6 are 12. Again we have 6 is in the units place. It is divisible by 2. That is 2 2s are 4. 2 3s are 6. So we got 23. So 23 is also again what it is? A prime number. It is also what? A prime number. Therefore the prime factorization of 92 is equals to 2 into 2 into 23. That is 2 square into 23. 2 square into 23. Now LCM is equals to LCM of 510 and 92 is equals to, so what is LCM? It is the product of the greatest power of all the prime factors. Greatest power of all the prime factors. Identify here what are the prime factors which we have here. It is for 510, 2, 5, 3 and 17. Here for 92 it is 2 square, 2 is there and 23 is there here. So for 2, which is the highest power, here 2 is there and here it is only 1 is there. So the product of 2 square into the product of all the prime factors with the highest power. 5 is there here and here we do not have 5, therefore we multiply with 5 and similarly 3 and similarly it is 17, then it is what? 23. So we should find all this multiplication and we get that LCM of this 510 and 92 is equals to what? The 2 square into 3 into 5 into 17 into 23. Multiply this. 2 square means it is 4. 4 into 3 it is 12. 12 into 5 it is 12 5s are 60. So 60 is multiplied with 17. 60 is multiplied with 17. So 17 zeros are 0. 17 6 are 102. 17 6 are 102. Then 102 is 1020 is multiplied with 23. So multiply with 3. 3 zeros are 0. 3 2s are 6. 3 zeros are 0. 3 1s are 3. With the 2 zeros are 0. 2 2s are 4. 2 zeros are 0. 2 1s are 2. That is 0, 6, 4, 3, 2. How much it is? 23,460. 23,460 is the what it is the LCM of this 510 and 92. Now HCF is equals to HCF of 510 and 92 is equals to the product of smallest power of the common factors. What are the common factors for prime factors for 510 and 92? It is 2 is the common factor, and for 2 the smallest power is there, it is only 1. Therefore HCF is equals to 2. Now verification. So verification we need to do for that statement. Verification. What is verification we have to do? LCM into HCF is equals to product of two numbers. Product of two numbers. Product of two numbers. So right, it is LCM into HCF is equals to product of two numbers. LCM it is 23,460 into HCF it is 2, that is equals to 510 into 92. So now here you can multiply with the 2. 2 zeros are 0, 2 6 are 12, 1 is there, 2 4s are 8, 8 plus 1 9, 2 3s are 6, 2 2s are 4. 46,920 we got the product of LCM and HCF of 510 and 92. Now multiply this product. 510 is multiplied with 92. So 2 zeros are 0, 2 1s are 2, 2 5s are 10. 9 zeros are 0, 9 1s are 9, 9 5s are 45. That is equals to 0, 2, 9, 6, 4. So how much we got? 46,920. So that is LHS is equals to RHS. Hence it is verified. Hence it is verified. Hence it is verified. So like this we will find the LCM and HCF of the given numbers. Then we can verify the product of LCM and HCF of the given two numbers with the product of two numbers. Is it clear, children? How to find the LCM and HCF? Now we will discuss exercise number 1.2, the third bit. Find the LCM and HCF of the following integers by applying the prime factorization method. The previous one we have used only, it is given only two numbers, and here it is given three numbers. We have to find the LCM of 12, 15 and 21 and the HCF by using the method of prime factorization method. So the first step it is write the prime factors for the given numbers. So prime factors of 12 it is so 2 6 are 12, 0, 2 3s are 6. Therefore 12 is equals to 2 into 2 into 3. that is equals to 2 square into 3. 2 into 2 it is 2 square into 3. Similarly, write the prime factors for 15. For 15 it is 3 5s are 15. So 15 is equals to 3 into 5. 3 into 5. Then the prime factors for here it is 21. 21 prime factors are 3 7s are 21. That is 21 is equals to 3 into 5. So 3 into 7. 3 into 7. Now what is HCF? HCF is equals to the product of the smallest power of common factors. So identify the first common factors for 3 numbers. So here 2 is the one prime factor and 3 is there. Here 3 and 5 and 3 and 7 is there. So what is the common factor for 3 numbers? And it is 3. And which is the smallest power of 3? It is only 1. We have only one factor is there 3. Therefore the HCF is equals to 3. HCF is equals to 3. Now LCM is equals to product of the greatest power of prime factors. Greatest power of all the prime factors involved in the numbers. So here what are the prime factors which we have? 2 is there, 3 is there, 5 and 7 is there. What is the highest power for 2? It is 2 square only. It is for 12 only we have prime factor as 2 is there. Therefore the highest power is the 2. Therefore it is 2 square into. Next prime factor you take 3. We have only power it is only 1 is there. Therefore the highest power is 1. Hence it is 3 to the power of 1 and or just it is 3. Then 5 is the other prime factor. For 5 only 1 is the power, therefore it is 5 into 7 also we have only 1 7 is there. Multiply, that is 2 square is equals to 4. 4 into 3 12. 12 into 5 12 5s are 60. 60 into 7. So 7 6 are 42. 420. Therefore LCM is equals to what it is? 420. LCM is equals to 420. So what is HCF? HCF is the product of the smallest power of common factors. Here the common factor is there, only 3 is the common factor and it has 1 is the power, the smallest power itself is 1. Therefore HCF is 3 and LCM is the product of highest power or the greatest power of factors, that is prime factors, not common factors. All the factors you should consider. So here what are the all together for 12, 15 and 21, what are the prime factors? 2, 3, 5 and 7. Observe their highest power. The highest power of 2 is there, it is 2, that is 2 square. Therefore 2 square into. Next prime factor is 3 and its highest power is 3. Therefore it is multiplied with 3 only or 3 to the power of 1. Similarly 5 and 7 we have only one factor is there, their power is 1. Therefore it is multiplied with 5 and 7. Hence it is 2 square into 3 into 5 into 7 will give you it is 420. So LCM of 12, 15 and 21 is equals to 420. HCF it is 3. Like this we will find the LCM and HCF using the prime factorization method. Is it clear? Now fourth sum from exercise number 1.2. Given that HCF of 306 and 657 is equals to 9. Find LCM of 306 and 657. So here HCF is given and two numbers are given. So given numbers are, what are the given numbers? Given numbers are 306 and it is 657. HCF of those two numbers is given as what? 9. What we need to find? We have to find LCM. The LCM is how much? So we know the two numbers 306 and 657 and they are asking you to find the LCM. So LCM we can find by using the prime factorization method. And it is given HCF is given, 9 is given. So use HCF is equals to 9 and find the LCM. There is a relationship between product of two numbers and product of HCF and LCM. So what is that relationship? It is we know that. So what we know? We know that it is a product of LCM into HCF is equals to product of two numbers. Product of two numbers. So here, so LCM we wanted to find LCM into HCF is equals to 9, and the two numbers are what? 306 into 657. Now we wanted to find the LCM, therefore it is 306 into 657 divided by 9. So do the calculations. 9 ones are 9, 9 threes are 27. 30 minus 27 it is 3, bring 6, 36. 9 fours are 36. That is equals to 34 into 657. How much we'll get? We'll find out. So therefore LCM is equals to 34 into 657. So multiply 657 with 34. 4 sevens are 28, 2, 4 fives are 20 plus 2, 22, 4 6 are 24 plus 2 it is 26, 3 sevens are 21, 3 fives are 15 plus 2 it is 17, 3 6 are 18, 18 plus 1 it is 19, therefore it is 8 and 3 it is 3 and 12 2. So how much it is? 22,338 is the LCM of 306 and 657. So we used the concept of product of LCM into HCF is equals to product of two numbers, and we have simplified. We got LCM is equals to 22,338. Like this we will find out when we know the HCF and two numbers. We can find the LCM. Similarly, you can find HCF when we know the LCM. Is that clear, children? Yes? Now, we will discuss exercise number 1.2, the fifth bit. Check whether 6 to the power of n can end with the digit 0 for any natural number n. For any natural number n means 6 to the power of 1, 6 square, 6 cube, when n is equals to 1, n is equals to 2 it is 6 square, n is equals to 3 it is 6 cube, or n is equals to 4 it is 6 to the power of 4. So whether this 6 to the power of 1, 6 square or 6 cube or 6 to the power of 4 and etc. will they end with the digit 0 or not is our question. Now any number, see the numbers with ending digit is 0, we have 10, then we have 20, 30 or 100 or it is 1000 or it is 990, like these numbers are there. What is the prime factorization of these numbers? 10 can be written as 2 into 5 and 20 means it is 4 into 5, that is 4 can be again 2 into 5 you will write. So the prime factorization of 20 it is 2, we have the prime factors 2 and 5, and the prime factorization of 30 it is what are the prime factorization of 30 it is 6 into 5 we have 6 into 5, 6 5s are 30, that is 6 means it is 2 into 3 into 5 it is. So again we have 5 is there in the one of the prime factor for the numbers 10, 20, 30, 100, even if you take any number ending with 0, it will have the prime factorization will have 5 is one prime factor. So from this what we can conclude? The prime factorization of any number if it contains 5, the prime factorization of any number if it contains 5, then that number will end with 0. So here we will solve this by using the prime factors of 6. So 6 prime factors of 6 it is prime factors of 6 is equals to 2 into 3. Since the prime factorization of 6 has no 5 as the prime factor, has no prime as the has 5 has it is the prime factorization of 6 has 5 is not the prime factor, therefore 6 to the power of n, that is equals to 2 into 3 whole to the power of n. Here the prime factorization of 6 we do not have 5, therefore 6 to the power of n does not end with end with digit 0, does not end with digit 0, for any natural number n, 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 6 to the power of n does not end with the digit 0. Like this question, check whether 12 to the power of n, 12 to the power of n, will it end with a digit 0 or not? 12 to the power of n. So the prime factorization of 12 it is 2 into 3 whole to the power of n. Again here also we don't have 5 as the prime factor, therefore 12 to the power of n also will not end with the digit 0 for any natural number n. So here also we used the concept of fundamental theorem of arithmetic. So by finding the prime factors of 6, we can say whether it is the number will end with 0 or not. If it contains 5 as one of the prime factor, definitely those numbers will end with 0. Is it clear, children? This is today's class. It is check whether 6 to the power of n can end with the digit 0 for any natural number n. Is it clear? I think today's concept is clear to you. And today's homework is exercise number 1.2, question number 1, second, fourth and fifth bits, question number 2, 1 and 3, question number 3, 2 and 3, question number 6 and question number 7. Complete the given homework in the notebook, and thank you very much.